This is good. Able to hear you clearly.
Okay.
Maybe we'll wait for 1 or 2 more minutes. Ganesh, is that okay?
Yeah,
I think
that's
more
fine.
students are just joining.
Sure,
Yeah.
sure. So are you able to see the slides properly? There's an issue.
Yes, it's clearly visible. Maybe we can get started. Okay, shall we start, Ganesh? Is that right?
Yeah, I'm fine from my end.
Okay, I think, yeah, maybe
I think we should start.
Yeah, okay. Good evening, everyone. Thanks for attending the first CMind seminar series talk, which is also doubling as a first talk in the CSC department. I'm very happy to introduce our first speaker, Professor Ganesh Ramakrishnan from the CSC department. And today he's going to be talking about his recent work on data efficient machine learning. So over to you, Ganesh.
Okay,
By
so
the way, Ganesh is also associated faculty in CMind.
Yes.
yes.
And he's also serving as the professor in charge of the new Center for Digital Health.
Thanks for the generous intro. Can you see the slides or there's some problem?
No, now it's not visible.
Okay, something went wrong. Let me know when it comes up again.
Not yet. Mm.
Is it the host control setting?
Sorry, the slides are not yet up.
I think
No,
so.
they're not visible. So I've
No.
made you are the presenter.
So,
Can you stop sharing and share once again, sir? I mean, if that helps.
okay.
Yes, it's visible now.
Yeah.
Okay, thank you very much for the generous intro. So this talk is about our platform, data efficient machine learning, and the underlying research. So why this talk? One goal is to present our open source toolkits in this space. It's called Distill.org, which is released under MIT license. But also the goal is to encourage people to build upon these in two ways, at least. One is we can work together to introduce new algorithms into these and also use these toolkits in your applications. So deep learning has seen a lot of traction through multiple modes. One is through improvement in the models themselves, as you can see here, compared to older algorithms with large amounts of data. Deep learning models are getting nearly human performance. This is in multiple domains, whether it's image processing or speech recognition, and this is largely also because of some superlinear complexity that these models have introduced, right? So you can see the growth here, and also the attendance at different conferences and workshops has been actually growing over years. So this is overall unprecedented participation. However, is the problem solved? So there are some key problems with large data sets and these massive models. One space is compute efficiency, the staggering training inference costs. But there's also data efficiency, which is, it basically requires a lot of human labor to label. But even that has caveats, because you may have biases in the way humans label, inconsistencies and noise. So here's an example you see below. You can have web label noise when you try and create cheap labeling, where you introduce the label that the web search engine already has inherently, right? So there are a lot of fragility to biases in the data, and overall there's an information overload, both labeled and unlabeled. So the compute intensity reflects in cost, of course. For example, training a BERT model on Wikipedia book corpora data set is 15 million INR roughly, right? Or deep model for NLP with network architecture search. NAS stands for network architecture search, where you're searching across multiple network alternatives. So you can also compute these in GPU days. For example, the Elmo model, which is used for contextual embedding in text, or the YOLO model, which is used for combined object detection and recognition. Again, on V100 GPU takes 8 days. So we can also measure the cost in terms of carbon footprint, and it's non-trivial. So I mean, if you look at the sustainable development goals push, right, then this is certainly alarming, given that there is a phenomenally larger cost in training a transformer as compared to a round trip flight between New York and San Francisco. So the labeling cost is another big worry. I kind of alluded it to earlier. For some domains, the cost is maybe lower. For example, image data set for classification may be low, but as the cognitive load increases, you'll find that the cost also increase phenomenally, sometimes by a factor of 10. So this talk is about data efficient and robust machine learning, and we identify all the places where efficiency could be improved: data preparation stage, model training stage, or validation stage where you're doing network architecture search, hyperparameter tuning, and finally, even in model deployment. Of course, now with the advent of TF chips, TensorFlow chips, you could probably delegate some of the algorithmic efficiency to hardware efficiency. But nevertheless, we would like to do our best on the algorithm front as well. So a common framework we're going to leverage in both our platform and also the algorithms is of subset selection. And why do we do that? Well, if you have large set of points, large space of architectures, or a large space of hyperparameters, we would really like to identify some subset. For most of the talk, we'll be really addressing subsets of points. So think of these as data points for most of the talk. And you have some information function f, which reflects some cost, right, or informativeness of a subset of points. This entire set is called the ground set V, and we are interested in doing a subset selection. We'll be using properties of subsets or of properties of functions on subsets in the form of submodularity and information theory for most of this talk. So submodularity, which I'll kind of define in a few minutes, and information theory. So from a subset selection viewpoint, there are kind of two blanks we try and fill up. We are interested in selecting subset of dash for a particular purpose. So the second is a purpose, and the first is basically about the ground set V that we alluded to in the previous slide. Now, depending on whether the subset is, say, a labeled set or an unlabeled set, when we say labeled, we mean the desired predictions Y for instances X are known, and unlabeled would just mean we have the X is known. So typically in a cold start setting where you don't have too much labeled data, you would be interested in basically identifying a subset of the unlabeled points. And if you have a warm start setting, you would be interested in identifying a subset of the label points. Okay, I'm sorry, this is the arrows got reversed. So these are reversed arrows. So we can also look at subsets of model parameters, subsets of architectures, and so on. So we'll try and divide up our platform in terms of cold start and warm start settings. There's been a lot of research in these directions these days. So overall, people have looked at Coresets. People have looked at information theory, also information-theoretic functions, and submodularity. But overall, there's been a lack of benchmarks and toolkits in this space. Algorithms such as greedy, lazier than lazy greedy, all of those have evolved in the space. But then benchmarks and toolkits is one big lacuna. And that's what we are trying to address here. So this is how we divide up Distill. The first, I would say, the most fundamental component of all of these is the submodlib, which is about summarizing massive data sets using submodular functions, submodular optimization. Some of them are not necessarily submodular functions, but they behave like submodular functions. The algorithms give you guarantees which are mimicking submodular functions. So we use submodular in a slightly generous sense in this talk. And I would like to acknowledge that a large part of this work was done by my PhD student Vishal Kaushal, who's also fortunately there on the talk today. He's done an excellent job building this model, and this has been used by us along two pipelines. One is a cold start scenario, which is where you have unlabeled data but very less labeled data. And the other was a warm start scenario where you have some amount of labeled data to bootstrap around, and you're trying to increase that in a very principled manner. So let's start with submodlib. And with that, we also introduce the notion of submodular functions. So as you can see in this simple illustrative example on the right, prototypical example is of a submodular function is when you associate, say, the earn with sets. So we have the set A and set B, and you can see that this B is a superset of A. And here you have this one ball which is being added to each of these urns. F, the function, measures the number of distinct colors of balls in the urn. So the distinct number of colors of balls in the urn certainly increases its monotonic function, but besides that, it also has this interesting property of diminishing returns. As you increase the elements, number of elements in the set, go from A to B, the additional benefit you get is diminishing. So in some sense, submodular functions do behave like concave functions, for those who are familiar with concave functions on continuous spaces. But here the issue is that we are dealing with a discrete space on the x-axis. But then they have some very nice properties. These functions, we'll see lots of examples of these. They're quite ubiquitous, and besides that, there are some very nice efficient algorithms. Now, as far as using those is concerned, I mean, Vishal has made it very easy for all of you. So this it's available as part of the Distill team, the submodlib library, and you have excellent documentation there. Using it is as simple as a pip install. Okay, so let's now get into types of subset selection. So this is a bird's eye view of what we'll delve into. You might be looking at subsets which represent the entire ground set. This is a ground set V, and here's a subset that we seek. So these are the ones marked in red are the elements of a subset X. So in the case of representation function, you are seeking an X that basically maximize the ground set well. So think of the representation in terms of representing clusters. So you want to really represent each cluster of set of points here. On the other hand, if you might be interested in a function which measures how diverse the subset X of V is. So in this case, you're trying to pick elements from clusters, but not necessarily represent every cluster. In fact, two clusters here are very close by, and therefore we have picked only one from them. As you can see, only this one has been picked, and an outlier has also got picked because we want diversity. On the other hand, you may look at coverage of concepts. So here are concepts: male, car, greenery, and so on. So we'll give examples of functions of each type, but now interestingly, you could also use these functions in some kind of conditional sense. You may want to get this subset X, this is X1 and this is X2. You want these subsets possibly conditioned on a query queue. This is a ground set. So you have a query which is, say, person, or you may want it conditioned on some privacy elements, person. So what we mean is that X1 here in the first case is a subset which represents persons more than any other element, whereas X2 tries to hide information about person. This is a case of privacy preserving. Now, how do you really materialize these is what we'll talk about. So let's go through some instantiations of set functions. Representation functions. Examples are facility location. Most of you have probably heard about k-means, but k-means finds arbitrary means. But now think of bedoid, which coincide with points in the space. So that's what facility location gives. We'll run through visuals. Then there are diversity functions and coverage functions. So there are largely three categories you could think of. Besides, you have set functions which are simple ones, which are like linear functions, where the f of x is the summation over all elements in x of some modular function m of x. Okay, so there's no diminishing return, it's just linear increase. Now we're going to pivot on information functions, and all of you probably heard of information functions, mutual information, conditional gain, etc. But we'll build all on these information function variants of these basic representation, diversity, and coverage functions. And there are also others which we'll not talk about: discounted cost functions and so on, cooperative cost, saturations, which is obtained by kind of clipping the functions, right, with respect to some saturation level. But we will not really have the time. There's too much already on the agenda. And then there are other complexity functions which look at cooperation between points that are selected. But let's just look at representation functions to begin with. I'm sorry, before we look at representation function, we look at information functions, which are going to be composed with representation, diversity, and coverage functions. So all of you have come across this most basic definition, right? Entropy of a random variable, and here we are showing discrete random variable. It's basically sum over all values it can take of probability of xc equals x into log of pxc equals x, right? This is a discrete version, and you can come up with a continuous version. But we'll focus on the discrete version. Now, it turns out that this function, this discrete entropy, is one of the canonical examples of a submodular function. And you've probably also seen this expression. So you can look at not only entropy of a random variable, but you can look at, for example, this difference, which is called the conditional gain. So this conditional gain highlighted here in yellow. which is basically looking at the gain in adding an element E to an existing set A. Now it turns out that this conditional gain is monotonically increasing, and because it's increasing or non-decreasing rather, it turns out that entropy is submodular. But this conditional gain itself is of interest, and it'll be interesting to see if you replace this h, the entropy function, with some other submodular function, what the results are. So this is how we play with submodular functions and create variants which are query relevant variants and privacy preserving variants. So imagine just replacing the entropy function here f with another submodular function, and we'll again delve into those. So you've seen mutual information, which basically is defined as f of a plus f of q minus f of a union q, which also could be written as f of a given q minus f of a, if you want to borrow from conditional gain definition that we mentioned in the previous slide. So mutual information just shows how relevant a is to q. Right now you can replace f with a submodular function and basically get other notions of relevance beyond just entropy. Likewise, you could also look at conditional gain, which says, okay, given a query which I want to be kind of agnostic to, what's the gain? Right? So this measures irrelevance to set P. Could be a privacy constraint, and we'll see examples of these. So and we'll also try and take a canonical example. So let's say we have this query set. I'll focus more on the query based. Privacy preserving just follows. So let's say this is my query set. An image of a dog, an image of some structure. It turns out to be a church here. And if you look at the TST plot of a bunch of images that you're trying to retrieve from, these are the clusters. There's a cluster of golf images, there's a cluster of truck images in red. In yellow, you have parachute images and so on. So they're very well separated. And let's see what happens if we subject the query based information measures to the submodular functions that we're going to talk about. So first class of submodular functions is representation functions. These are characterized by a similarity kernel. So you're looking at similarity between pairs of points. And the simplest example is a facility location, where think of trying to locate facilities. The points in red is what you're trying to locate, such that you are representing the points in green well. The representation is measured through the similarity function SIK. So you're basically seeking these K facilities, and you're seeking these K facilities for all the points I in the ground set V. Okay, so that's basically sum over all points of the max similarity of a point in the ground set to the K. So you want the closest time. So this is like K-medoid clustering. Okay, so it turns out that this facility location is a submodular function. It has that diminishing returns property, which we mentioned earlier. So what happens when you apply it to a bunch of images? Basically, you'll get the centroids. This is the class of representation functions. Now there is saturated coverage, which also is a representation function where you have a threshold alpha I on the similarity. Graph cut is an interesting variant where you look at not only representation, you have this representation part, but you also subtract out self similarity. So it's kind of indirectly saying I want some diversity as well. Okay, but we'll see more of diversity later. But largely this is what all these functions give you. They give you these good centroids. So they pick centroids. Now what happens if we subject this class of representation functions to information measure? What we mean by that is we basically are conditioning them with a query, right? So let's look at the mutual information version of facility location, the first function here. And now there can be other, again, variants of that. So we won't get into the details here, but for example, you might be looking at a mutual information version which is grounded in the set V that you want to represent. So we call it FLVMI. So the ground set. So, but the key here is that you want to represent the query well. So it does pick up few query relevant instances. You can see in response to the query of dog in the church, you got some query relevant instances, but it tends to get saturated. It's very happy with just 3 images here, 2 from dog and 1 from church, and then just picks up a whole bunch of other images which are basically just basically trying to get some diversity. So otherwise it's representing both the centroids well. So what happens now if you move from the ground set V to the query? So this is another variant of mutual information which is grounded in the query set, and this gives you highly query relevant retrieval, but somehow now, because now you started focusing more on the query, the bias in the query, in the population with respect to the query, will also start reflecting, and you find that unfortunately there are more images, somehow in the feature space related to the dog than to the church, and therefore there are more dog images, right? It's very query focused, this version, because it's supposed to be query focused, FLQMI, but unfortunately it's just biased by terms in the query. Okay, so there are other variants I will talk about, but so let's take the example of diversity functions. So diversity functions are purely based on diversity of the retrieved set, and a very classical example is determinantal point process based functions, a logdet. So what is this L? This L is basically a subset of the similarity matrix, subset pivoted on S, the set S. So S is a subset of V. All of us know the relation between the determinant and the volume of the points that the matrix whose determinant you compute is representing. So you could think of this determinantal point process as capturing the volume. So the higher the more spread out the points, the more diverse the points, the larger the volume. Okay, so this similarity kernel LS that we have shown here, if you take a subset which is diverse, then you'll get more volume, and therefore you have the highest chances of maximizing diversity functions. So here's as I said, there's a subset of points that is picked up by maximizing DPP, and even though there is a cluster here, this is basically seashore images in contrast to sky images, right? But because both of them have blue backgrounds, you found that it's content basically picking one image from this combined set, and it's actually it's biased towards this outlier which has no cluster of its own as such. It's just a singleton. So it's picking basically items as different as possible. There are other diversity functions, dispersion, etc., but now not all of them are submodular. In fact, there's only one version here, this slide, which is submodular. So this dispersion sum is not submodular. Dispersion min is not submodular, but there's something called dispersion min sum, which turns out to be submodular. This is again picking diversity. So it's looking at dispersion min, for example, is looking at let's say you're maximizing, you're interested in maximizing the minimum pairwise distance between any pair of points, right? Now, even if it's not submodular, there are some very good greedy algorithms which give you good approximation guarantees. So, for example, half approximation guarantee through a greedy algorithm is possible for dispersion min. Okay. Now let's see what happens if you apply mutual information to one such diversity measure, and you find here that the expression is shown here. Now you're looking not only at the similarity between the points in the selected subset, but you're also looking at similarity within the query points. And the same is observed with mutual information. Even though the query is dog and church, the focus here is actually more on diversity. It's landed up getting dogs with different poses. It didn't really, and that's because the image collection had more dogs. It's of course sensitized itself to the query, but unfortunately church is nowhere here. So it's banked more on diversity with some representation of the query. So likewise, we have many other submodular functions. There is coverage, where you're trying to cover the elements. All of us have gone through a basic course where we learn set cover functions. So you're trying to cover these features by picking the right set of documents. Okay, so dog, cat, bird, man, beach, etc. So these are keywords which you're trying to capture through these documents. Now it's possible that some of these keywords have more weightage than the others. So you're trying to cover concepts, and you could optionally cover concepts with higher weightage. And so this coverage is through this bipartite graph. You can see what is matching, which document set is matching which set of words. You can have a similar kind of notion of coverage when you're looking at images, either objects or in the feature space. But the basic idea is selecting instances which cover all concepts. So you could also have probabilistic versions of these. Probability that an image I covers a concept J, and this is a kind of noisy OR extension. You want to basically maximize the probability of covering the concepts, at least one concept being covered by the image. So you could also extend these now with slightly non-trivial extensions. For example, concave over modular functions. So concave functions such as square root, you apply it on a modular function that turns out to be submodular. And again, we see that you're getting highly query relevant results, and they're trying to represent all of the points here. So that's very interesting, because the focus is somewhat on the features here. So all the images have to do with either a dog or a church, but in that process try to get some diversity. So it's all of these functions now behave differently just based on the focus. And you can likewise have feature based functions. You're trying to, for example, look at the contribution of a feature in a set of image set S through let's say a penultimate layer in a deep network. Okay, so you can come up with deep submodular functions, and this deep submodular function is banking on concavity properties, the concave over modular property that we discussed earlier, which leads to submodularity. So you can basically have now compositions of these. So summarily, we talked about some modular functions. Some of them are actually even monotone, and monotonicity yields itself to some better approximation guarantees with respect to greedy algorithms. Some of them are non-monotone. For example, log determinant is non-monotone. Graph cut is not monotone for lambda being less than 2. But lambda was basically the trade-off between the similarity of a point from a cluster, from the selected set to all other points with respect to the self-similarity. So lambda is that trade-off. So there are also non-submodular functions which I mentioned. For example, disparity min and disparity sum, for which greedy algorithms still work reasonably well in practice. Okay, so this is like a bird's eye view of information function classes. I won't get into the details, but this is what we have kind of shown so far. This is like flashing in front of your eyes, a summary. We have looked at the query based ones. This is the query based ones. We looked at these. What we did look at was a privacy preserving class. But I can imagine, I'm assuming we can imagine how you're going to get counterparts where now, instead of retrieving images from the dog and the church class, you're trying to hide the information about dogs and churches, or for example about anything that's of importance from a privacy perspective. You could also have a combination of these where you're looking at query sensitivity and privacy preserving, just agnostic to the information in P. So we'll talk more about the applications of these, then get into math details. Maybe probably in a future talk we could have more details on more deep dive. So this is the summary. We have 3 classes of functions: representation, diversity, and coverage. And for all of these, you can compose with them with information functions to get query focused or privacy preserving summarization. Now, what about the algorithms for optimizing? So the general algorithm, the general optimization framework is you're trying to maximize a function f over the subset A of the ground set V, subject to some selection cost on the ground set A, sorry, on the selected subset A. For example, this simplest example could be that you're looking at the cardinality of A. So F, we would like that it's monotone submodular, but at times it's also non-monotone submodular, and dispersion functions we've seen are also well-behaved functions from a greedy perspective, greedy algorithms perspective. And we'll typically assume that the selection cost is modular. Okay. So the simplest algorithm is the greedy algorithm here, and you're basically selecting the next element E, which maximizes the function f, right, post inclusion into the set Si. So you're just greedily growing the set Si. Right? How good is this set Sk? Well, it depends on what the constraint set is. So let's say looking at cardinality constraint. So it turns out that under that condition, you can come up with some approximation guarantee. In practice, it's pretty good. And so you can see optimal in green and the greedy is in blue here. So it's pretty close, within say 95% of the optimal. This is in practice. And here's the use case, trying to place sensors to cover different measurements on a field, right? And each sensor placement leads to some coverage. So coverage, as I said, is one example of submodular function. And you greedily kind of introduce sensors at those locations which have maximize the remaining part to be covered, right? And that turns out to give you a reasonably good solution, almost as good as optimal. But it turns out that in theory as well, there is, I mean, I won't say the most exciting, but a very interesting characterization of the approximation guarantee. It is 1 minus 1 over E times optimal solution. So you have at least that much when you're trying to maximize. This is at the optimal solution Sk. Sorry, the obtained solution Sk with a budget of K. It also turns out that there's no polynomial time algorithm that can do better than FSK in the worst case. So this greedy algorithm is actually a good greedy algorithm. But you can also have other constraints. For example, you could have cost constraints which are different from cardinality. So in which case there are variants which look at a combination, a hybrid of greedy algorithm and a modified greedy, which looks at a weighted version of the gain. So this FSI SI union E minus FSI, this is what we are already familiar as the conditional gain, EI given S. Now you divide the conditional gain by the cost and pick the E star, which is the next maximizer. Right, and this just reduces the approximation factor by a half. But in practice, again, it's even better. More importantly, there have been other other more effective algorithms which are slower. But yes, this is something we implement in the submodular package. So summarily, there's a problem formulation and the greedy algorithm framework which we implement in submodlib, and the use of submodlib with the choice of these algorithms and also the choice of information functions with slapped on top of these different notions of representation, diversity, coverage captured through suitable submodular functions is very easy to use. It's just a few lines of code, as you can see here. So you can pick a ground data, the V from where you're selecting the subset, but you may have the query Q which comes from a different subset. And you basically can also choose the greedy algorithm. And what I explained was naive greedy, but there are versions like the lazier greedy, lazy greedy, which gives you exact solution for the submodular case through a kind of branch and bound search. And those algorithms are all exposed here. And as you can see, if you just did generic summarization on the set of points in this square, in this rectangular plot, you basically land up picking these points here, right? There's no query, so you just get some kind of diverse set of points using facility location. You're not just diverse, you're also trying to represent the points in the set. Whereas if you looked at facility location with mutual information, a simple few lines of code, but you now see these are the query points. The points in green are the query points. And you find that the algorithm has not picked any point from these two clusters because they're too far from the set of query points. On the other hand, the moment I put a privacy constraint, no point from this cluster has been selected. So this kind of repels the selection of points from that cluster. So this is how easy to use it is. So you can try it out yourself. Now we'll quickly move on to other modules that build on submodular. The first being trust, which is focused on a cold start setting. So trust builds on very naturally on the information functions, specifically the query-driven information functions. Very easy to use, and here's a use case. So imagine that I have a large unlabeled data set. Think of this as my ground set V. And let's say I specify to it a query set Q. So as you can see, these seem to be like nighttime images. Night images. And based on these, now we are able to find a subset, say A, which kind of maximizes the information function between A and Q. So this is a very natural use case in cold start settings. Let's say I have a large unlabeled set, and I have few images which I know is going to be of my target interest. And I could just select the subset and ask the user to label these. That creates my targeted subset T. And that could be augmented to an either existing or an empty labeled training data set. So that's why it fits the warm start setting pretty well. So this is a very easy to use package, just builds on what we have discussed so far. This can also be used when you are iterating on confusion matrices. I'll come to that in the next slide. But the usage is as simple as submodular itself. So I already gave you this one use case where you have the unlabeled set as V and the target as Q. But you could have other cases where you're iterating through, say, a performance evaluation on through a confusion matrix. And let's say there are some false positives or false negatives that catch your attention. You would like to reduce them. So in this case, this false positive or false negative set can become your target set Q. And you could do subset selection either on the validation set or the training set. Another use case is when you're trying to do targeted selection for, say, personalization or customizing, say, handwriting digit recognition to a specific user, a particular deployment scenario. So this becomes very interesting in, say, OCR settings or handwriting digit recognition settings, things that I work very closely in. So these are some use cases of trust, and the algorithms implemented in addition to the submodular diversity representation coverage. We've also made the usage of the submodular easy through relevant abstractions in the form of query relevance and diversity. For example, where you're trying to look for rare class, you're trying to capture examples to be labeled which are aligned with some rare class. I gave one example, nighttime images. Or instead of a target set Q, a query set Q, you may have a privacy set P. So you may want to pick points which are not very close to the outliers. You may in fact have some labeling functions or some human rules which have already done a fair bit of the job, and you really want the subset to be labeled to be far from rules, far from the examples that the rules cover. And that's what that's another application we'll talk about next. But you get a glimpse of how trust also lets you benchmark. So there are different log date, facility location, the two versions we talked about, graph cut, and so on. So all of these, you can see that in general the use of these information function makes a big difference to targeted subset selection. All of these are actually quite dominant with respect to existing state of the art, but you're welcome to add your own new algorithm here and benchmark it against those which are already a part of trust. So I'll move on to another application, which again is a kind of cold start setting. It's called SPEAR, semi-supervised data programming. That's what it stands for. And the idea here is to reduce labeling efforts using data programming and subset selection. As usual, it's very easy to use, has extensive documentation, and a bunch of our BTech students and PhD students have actually built it over the last 6 months. What does it have? Basically, you can design something called rules or labeling functions. So here's an example. Let's say I'm interested in identifying if a question, I'm trying to do question classification. And what are the classes here? It could be a description question or it could be a numeric question. If it had a keyword such as how, it would probably be a description question, but if it's how long, then it's a numeric question. Now, obviously, how would also match numeric questions. There's some kind of overlap you can see between them. You could have more complex labeling functions. Here's an example which is looking at labeling function which identifies whether two x and y have a spouse relation or not. So these could be arbitrary Python functions. What we allow is very rich set of preprocessors, decorators for all of these, and we also have continuous scoring functions. That's some joint work I did with Sunita a year back through a master student. Those have also been incorporated here. Now all of these could be applied on unlabeled data. So you could just apply all of these on unlabeled data and basically get your tentative labels or weak labels, and that's what we call pre-labeling. So you could do that, and then you could run one of your favorite consolidation models, what we call label aggregation models, because these labeling functions could be noisy. You may want to learn parameters of those labeling functions. What we also add here is the facility to do semi-supervised learning. So instead of a standard paradigm where you're just trying to generate the label data and then forget the labeling functions, we let the user operate in a larger context where the user can have the unlabeled data, the labeling functions, and also some labeled data. And we'll come to that next. I'll take another example here with image exemplars. So all of you probably have used Google Album, right? And then you can actually label examples with exemplars. Right? This is a user-defined label which says this is my brother, to categorize uploaded photos. So now you could also write rules, for example, saying that add photos to an album X when the photo contains a person name. So the rules need not be always textual rules. These could actually be exemplar based. And you could also compose these rules. I mean, a bunch of family members put together. So you could create albums and let these get added to your photo categories. The issue, however, is that there could be incorrect examples, right? So some of these are wrong matches, incorrect matches of a particular person, Sundar. So what we provide here is different label aggregators. So now there are two paradigms for label aggregation. One is a cascaded approach where you say, okay, I have a generative model which takes the outputs of these different labeling functions and just generates the labels. And then you pass it on to a discriminative model which has nothing to do with the generative model, which has nothing to do with the labeling function, right? So these are two worlds. We also support joint approaches where the two can operate and coexist. And not only that, you can also prompt for labels, prompt for examples which need to be labeled. So these are some state-of-the-art algorithms, both cascaded and joint, that are supported here. So I mean, I'll just very briefly go over our version, which is a SPEAR from ACL 2021. So this is what we facilitate. So let's say you have the labeling function model. I tried to abstract the math using some color coding here. So you have some labeling function model and you have some feature model. what this allows you to do, this programming paradigm allows you to do, is that you could try and match the labeling function model and the feature model on your labeled data set or on the unlabeled data set. So the first component here of the loss, for example, says I would like my feature model to do to be very aligned with my ground truth. So there's a feature model and ground truth. The second says that the entropy of the feature model on the unlabeled data should not be high. The third component, which is very interesting, we say, oh, I could look at alignment between the feature model and the labeling function model on my unlabeled data. Or I could also look at the feature model and labeling function models alignment on a combination of the unlabeled and labeled data sets. In addition, we also provide for the human prior in the form of precision or quality guides on the labeling functions. These can also be obtained through validation set in the case that you have labeled data, but otherwise this can be just human priors. Now what we also bring is this labeled data, how can it be selected intelligently? So instead of these the labeled instances being generated in an ad hoc manner, can we use our subset selection paradigm for generating this labeled data? And here's an example. So instead of you could have your labeling function based exemplars in the Google album case, but could we be proactive about the examples that need human supervision? What we want is that the selected subset should complement and not really subsume the labeling functions. So how can that complementary action be enabled? And that's where recall that we have this privacy preserving notion of summarization. So think of selecting a subset A which preserve the privacy of the labeling functions which we have already at our disposal. So this is how we see complementarity. And here's an example. You have two labeling functions, LF1, LF2, and they seem to be in good agreement on the instances S1 and S2. They seem to, labeling function says that S1 has label +1, and labeling function 2 says S2 has label -1. This is for basically a YouTube spam classification task. However, these labeling functions are completely confused for on two other instances, S3 and S4. So either both abstain from firing, or both of them give the same label. I mean, give conflicting labels, both of them fire. So what we provision for is using our privacy preserving subset selection paradigm. You try to maximize, say, a function f of the subset A given the privacy set P, where the P is basically these labeling functions. And the set A that we choose turn out to be S3 and S4. So this is how we get complementarity. And that's what contributes to our robust supervised data programming. And at a glance, you can see how this kind of, instead of hand-picked examples, if the examples are governed by a privacy-preserving law objective, information measure based on some submodular function combination, we get significant gains. Just want to draw your attention to the last two rows where you're basically doing subset selection either in a supervised or an unsupervised manner. So I know we're running a bit out of time. Preeti, can I just run through the last two modules?
Sure. Yeah.
So the remaining two modules have to do more with the warm start setting, Coresets and data subset selection, where the idea is to bring robustness but also reduce end-to-end training time from days to hours, right? To hours to minutes, using notions of Coresets and data subset selection. And the idea is, if you have lots of these points, there's redundancy, there's really no points like picking all of them. So can you just be intelligent about the points you select here? And this we would like to do in an end-to-end manner, in conjunction with the model being trained. Again, the use of this is very simple. We have lots of benchmark algorithms implemented here. So here are some use cases. If you want to do efficient and robust supervised learning, just select the set of points which which would really make the difference, maybe points close to the margin. You could also use it in a semi-supervised setting. If you want to do hyperparameter tuning, lots of parameters to select from. Sometimes you can, a subset of the data can be more effective for hyperparameter tuning, even in terms of robustness. And finally, efficient network architecture search by using small subsets of the label data. So this is, of course, a lot of ongoing work. Some of this is also joint work that we are doing with IBM Research, some of Spear and some of CORDS as part of their AutoML platform. But here are some algorithms we have implemented, and few of those are ours. Glister and grad match is from this year. Well, Cellcon actually it's being integrated. It's not yet integrated. And then Vishal earlier on had worked on data subset selection based on submodular functions in 2019. So all of these have been implemented, and they're also benchmarked. So I'll just run through Glister as one canonical example of how CORDS, the paradigm of CORDS, and we kind of followed up in ICML 2021 with grad match. But the idea here is, if I have training data T on which I want to maximize the likelihood, and you're trying to obtain the theta star that maximizes the likelihood, but you also have validation data at your disposal. Now, could you make effective use of the validation data to do efficient training? Probably you don't need the entire maybe you can get this theta star S from a subset S of this entire training set U by leveraging signals from the validation loss. And that's the basic idea. Okay, so select a subset S of U such that the resulting model performs the best on the validation set. So the best evaluation is on the validation set. So what are the requirements for optimal subset selection? We would like the selection to be as fast as possible. So you really don't want that subset selection time really becomes a big overhead. And you also want some theoretical guarantees of subset selection algorithms. So, so how do we select the right data for efficient and robust learning? So here's the overall optimization problem. You're trying to maximize the likelihood on the validation data with respect to a subset S of the training data, which governs the parameters theta that turn out to be the optimal ones. So theta is star, which I mentioned in the previous page. So ultimate goal acid test is the validation loss, and that's how we often also do hyperparameter tuning. So now what happens if you use the full training data set? That's also that's another option. So all that follows through if you just replace V. You can also replace V with S. With U, the entire training set. So there are some class of problems for which the inner argmax can be solved in closed form. For example, if you have the naive base as a likelihood as a model and likelihood of the naive base, it turns out that under simple assumptions of known class priors, the naive base classifier just becomes a feature based function model. Right? We talked about the coverage based models. So this is submodular. And it turns out that if it's nearest neighbor, then it's a facility location function. Right? But unfortunately, this is not good enough for us. Why? Because the inner optimization problem will not necessarily be based on naive base or nearest neighbor. So in general, solving the inner optimization problem to completion can be expensive. And also, if solving in a closed form can defeat the purpose of selecting subset for faster training. So what are the approximations? The first approximation is you could approximate the inner optimization problem by taking a single gradient step. So this would probably click to anyone who is familiar with simple gradient descent optimization. Don't really look for the optimal solution. So this gives you the likelihood and the validation set in terms of this single step gradient. However, this is not good enough. Now there's some theoretical findings. if it turns out that when the validation log likelihood is either negative logistic loss or negative squared loss or negative hinge loss, then the above optimization problem becomes a cardinality constraint submodular optimization problem. So this is this so far so good. In one case, if you have a negative cross entropy loss, then you have something called weak submodular submodular function, weakly submodular function. I won't really have the time to get into that. I had some slides, but we'll have to skip them. But it suffices to say that this is very handy, because now you can look at deep networks. You can look at the last layer of a fully connected network, a convolutional neural network, because most of the times you'd be using either a logistic loss or a cross entropy loss, or if you're doing regression and a squared loss. Right, and the submodularity we've already seen, this natural diminishing returns property. So I'll have to skip this, the weakly submodular function, because that's only in the one case. So what happens is that this is not good enough. To get further speed ups, the issue is that you have to do a complete forward propagation on the validation loss, even with this one-step approximation. So instead of doing this multiple forward passes as you're selecting every element, so for the multiple forward passes are for each example X that we are adding to the set S, we need to do this forward pass, right? Even if you use a greedy selection algorithm, which we discussed earlier on. So here's another interesting approximation. We basically use a Taylor series approximation on the LLV, which is the validation loss. So this we are doing on the first order update, that the theta. And as you can see, there's only one element now on which you will need to basically access the training set with respect to the set S. The set S to which you're adding elements. The rest has been separated out. The validation components are separated out. What we're trying to do is reduce the cost overall in computing the optimal subset S by greedily adding the elements X to the set S. So this gives us a online framework, this Taylor series approximation, where we are not doing the subset selection at every step. Rather, we now have L epochs of the stochastic gradient descent. Then we do a greedy data subset selection algorithm, but this greedy data subset selection is on the Taylor series approximation. And then you go back and do a bunch more of updates, stochastic gradient updates. So this is the online framework. So data selection is done every L epochs, and we try different values of L, and it's pretty robust. So some more computational aspects which I'm going to skip here, but instead of selecting a subset every epoch, in addition to selecting every L epochs, we use only the last layer gradients, and there are also other variants of the greedy algorithm. For example, stochastic greedy selection does well, where you're not picking elements, the max element, but probabilistically with probability proportional to the value of that element, you're picking examples. So without getting into details, is what really this helps us is that if you have a full training complexity where based on a backward pass of B and a forward pass of F on an entire training data set N, and this N is the key. Now you don't have N into T anymore, right? So N is kind of decoupled from the T and the B. So that's the main finding. And this really gives us in practice a good speed up, but in theory also there's some interesting convergence analysis properties. Now what I would really like to draw to your attention is that our Taylor series approximation had this term which invoked the dot product between the validation gradient and the training gradient. So recall Taylor series here, and it turns out that this particular dot product, suitably normalized here, this has a very important bearing on the convergence, right? So the closer, the more aligned the training gradients and the validation gradients are, the better we can do, the faster convergence we have. So we can get convergence in 1 upon epsilon square, where you're basically trying to get an epsilon bound to this min loss over all the epochs. So this is the dot product also motivated some more works of ours where we tried and aligned the gradients directly instead of looking at any first order approximation on the validation loss. So that led to this is exactly what motivated our follow-up work, which was at ICML this year, called grad match, where we tried to match the gradients directly. But efficiency wise, this gives us a significant speed up. So, and for example, if I want a speed up factor of 7, then I have to basically bear with a test error drop, right? I mean, error increase of around 3 or 2.8 to 3. Right, but if I'm happy with a speed up of 2.5 to 3, then actually there is no loss at all. All right, there's a zero. There's no drop in the, also no increase in the relative test error. So these are interesting to note. And there are some again very interesting results for semi-supervised, but a very pronounced gain we get for hyperparameter tuning. Yeah, I leave you to read the papers for the insight, but the summary is that almost 3x speed up with no loss for both supervised and semi-supervised, and almost 10x speed up for AutoML, which is where you're trying to do hyperparameter tuning with no loss in accuracy. And robustness wise also, this, because we're looking at validation loss, we find that the model is fairly robust, but summary is at 5x to 7x speed up compared to robust learning algorithms while achieving comparable performance. So what CORDS offers you overall is not just grad match, but a whole bunch of other algorithms. I kind of mentioned Glister, and then there's grad match, which followed up, but there are many other variants of those, along with Craig, which was published at NeurIPS last year, sorry, ICML 2020. So you can actually profile and look at how they compare with each other in both in terms of speed up and error on supervised and semi-supervised. So this is CORDS, and last, maybe very quickly, I'll talk about Distill, the last module, which again focuses on the warm start setting, which assumes that you have some amount of label training data, but it also lets you grow that set. So I thought this was a very natural flow for the talk also, because now we have grown the data, but we all know that we have ever increasing changing distributions, right? So how do you adapt to changing distributions? How do you get more data labeled in operational settings? So all of us must have heard of active learning, but we call it deep, diversified, interactive learning, because we also are interested in doing end-to-end learning. So again, Distill, like all the other modules, is very easy to use and extensive documentation. But the goal here is you want to consult the Oracle labeler in a warm start setting and get label data and grow the data. So some very interesting properties of Distill is that besides having many state-of-the-art algorithms in PyTorch, by the way, I forgot to mention, everything is in PyTorch, entire platform is in PyTorch. It has a very important property, two important properties. One is it has implementations of several common deep neural networks. So you'll find it very easy to get started on your favorite end application. Equally importantly, what has happened is a lot of active learning has been profiled while not factoring in the effect that data augmentation could bring in. Right? If you augment data, let's say by flipping images, right, in a CFAR10 kind of setup, you often that often undoes the advantage that active learning brings in. So Distill also has common data augmentation techniques so that the generalization performance can be improved and you don't bank on active learning alone. So there are several state-of-the-art algorithms, and Glister, we have our own active learning version of Glister, which I'll just allude to. But there are many others. You're welcome to go and visit and try it out yourself. But since I talked about Glister, the active learning framework is a very simple extension there, where you're basically selecting the subset of points in every epoch to be labeled. So you're basically identifying the points that need to be labeled. This is the set to be labeled. But then the question could be, how do you do parameter estimation? So for the inner optimization, the parameter estimation is done using hypothesized labels, which means labels hypothesized using the previous iteration. So that's a simple modification and in Glister active, right? And I probably am running out of time. So, but the thing is, Glister achieves a 7x to 7x speed up at 10%. When you're looking at 10% of the full training accuracy, and 3x if you're looking at 30%. But yes, you're welcome to go and visit. I think we have totally run out of time, and you can also compare several state-of-the-art algorithms on not only accuracy but also labeling efficiency, which is basically the kind of throughput for every label example that I label. What is the gain I get in accuracy? That's it. And we actually made good use of Decile in some of our applications. So video analytics, we have had products which have got licensed, and it has also hit headlines and interestingly the newspaper articles also carry reference to Decile, data efficient learning, as you can see here. Times of India explicitly had a link to Decile. So far we have made use of that, but really want to make use of we have an active collaboration with IBM Research where we are making use of Decile. So these are impacts so far, but we really want to make an impact in many other fields. So OCR, machine translation, post editing, and some ongoing work with Preeti also on speech, personalized speech recognition. And then there are totally upcoming ones where I would invite all of you to contribute to the upcoming list. So thank you very much. Yeah, thanks for going a little over time. Sorry for going a little over time, and thanks for bearing with me. Yeah.
Thanks a lot, Ganesh, for a very comprehensive talk and introducing this very potentially impactful toolkit. So I welcome questions from the attendees. I think Professor Sunoj has one question.
Ganesh, it was really wonderful.
Thanks, Sunoj.
So the question or the point that caught my attention is you said that hyperparameter tuning could be benefited by using subsets. So in that, could you recommend whether if we were to select between representation, diversity, and coverage, all three is a must for this exercise, or you would recommend this being the topmost priority to be considered?
Oh, thanks for an excellent question. So let me just rephrase. Your question was, if you want to do hyperparameter tuning, what criterion for subset selection would be the most effective?
Yes, among the three: representation, diversity, and coverage.
Correct.
Assuming that we don't have the bandwidth to do all three together.
Okay, thanks for that question. So my general experience has been that if you're in a cold start setting, right? I mean, it's like a toddler, a child trying to learn. You would like to do representation well. I mean, you would like to represent the real world scenario. Because if you're going to confuse a toddler with too much diversity, that toddler will not learn anything. So in a cold start setting, I would generally recommend representation. But you already have a lot of data, right? And let's say hyperparameter tuning, I'm assuming you have lots of data already, right? In which case, I would say you could focus a bit more on diversity. For example, the graph cut function, which does kind of blend diversity and representation, I would recommend that.
Okay. Thank you.
Thanks for an excellent question. Yeah.
Hi, Ganesh.
Yeah, please.
I have 3 questions, but I think the time may not allow me. But let me ask you one question I'm desire to have answer. So this kind of subsample selection, right? So in generally, yes, we can see why it's very efficient for training the model. But a key question I would like to ask you, in real world data, right? The data is not always ideal, sometimes even actually quite dirty. So in this case, you will use this kind of algorithm can actually generalize after you're training the model for the real world data.
Correct. So how does it work in real world data? That's a question, right?
Right. Yeah, my question is, use this kind of selective sample to training your model. How that's whether the model can be generalized in the real world.
So our experience, at least in the video analytics, this is absolute real world. So I mean, the whole platform is driven by real world. So I'm sure as we progress, we'll find other real world settings for which we'll need to. Sorry, this just got. So I just wanted to show you the use cases in the video analytics setting. For example, we had these issues where we had training data was very different from the data in which we wanted to deploy, right? So in video analytics, we were able to identify the target using something like trust. So these are actually real world. Now the caveat there is, yes, if you're looking at anomaly detection, right, this classification at the level of frames or the videos, then possibly it can be easily deployed. But now if you're looking at object detection, right, within an image, what are those rare phenomena? I'm sure there'll be some significant extension that we need to bring in. But I would still believe that the libraries that we have, the core modules that we have, they are applicable. More helper functions will be required for certain sequence to sequence or structured settings when you want to do object detection within an image. So in that sense, for those real world, we'll have to build more decorators, more wrappers around what we have. But yes, algorithmically, there's a lot more to be done, and maybe on a specific use case, we will know what needs to be done on the algorithmic front. Did
Thank
that
you.
help?
Yes. Thank you very much.
Thanks. Thanks
So
for your
there's a
question.
question on chat from Abhijit. I'll just quickly read it out. So data augmentation is widely used to improve generalization and robustness of deep learning models, but cluster sounds like it's opposite to data augmentation. Is it possible to make both these approaches complementary?
Okay, that's an interesting thing. Yeah, so Glister basically hinges on finding a subset. Yeah, so there's a kind of assumption of redundancy, and that's a very good idea. We are exploring that with some of our collaborators. We're trying to see how there have been approaches to like mix-up, right? Mix-up does data augmentation. Can mix-up be seamlessly used within a Glister like validation pivoted subset selection framework on the training set? So that's very interesting. I'm myself invested in it, but if there are other thoughts, I'll be happy. I mean, other ideas, we'll be happy to see collaborations emerging from this talk. But nice suggestion, Abhijit.
Are there any other questions from the attendees? Okay, if not, I think we can wrap up. Thanks
Yeah.
again to everyone who attended the talk, and many thanks, Ganesh, for a really,
So
really
Preeti,
nice
can I
talk.
just add to one more point from Abhijit?
Please.
So I just mulling over his question a bit more. The other interesting thing which I didn't talk about much at all, which is a combination of privacy preserving and query sensitive. So Abhijit, I mean, let me just go back to that overarching slide. So if you look at this overall use case, right, we can have not only query relevant, but we would like to get maybe examples which are different from P, right? So we could also use this privacy preserving setting for data augmentation, and we haven't really explored combinations of these, though we be looking at these in isolation. So if you look at this combined information measure, I think there's scope for bringing together subset selection and augmentation. Yeah, that's all I wanted to add. Thanks.
Thanks again, Ganesh.
Thanks.
Thanks, everyone.
Thanks. Bye.